We're going to continue our work with the interpretations of the definite integral with a few examples here. So let's take a look. We have a problem where we have a pan of biscuits being removed from an oven, at which point time t equals 0. The temperature of the biscuits is 100. So I think that's important. The rate at which the temperature of the biscuits is changing is modeled by this function. So realize we're being given a derivative there. And we're being asked what is the value of b prime of 3. So we're going to use the calculator to do this. So I'm going to share my Desmos graphing calculator so you can see how I put this in here. And I'm going to type my function. Let's see, I'll do b prime of x equals, because I like to use the same labels. That way I don't get confused. Negative 0.173t. Oh, got to do x. Forgot about that. Desmos only understands x. And then friends, notice I can go to the next line and do b prime of 3. It's giving me an error here. Okay, so let's just label it f prime. And I don't think it wants to do the prime, so we'll do f. How about that? F of 3. There we go. So we got our value. Got to work with what we have here with Desmos. I get negative 8.236. And so watch my units. The rate the temperature is changing. So the temperature is degrees Celsius per minute. And then we're asked to explain the meaning of this value in the context of the problem. And this means that the temperature is decreasing at 3 minutes. And it's decreasing because the derivative there is negative. Now, we're being asked to sketch a graph. So I'm going to use my graph from Desmos. Now I'm going to zoom out just a little bit. It'll give me a little bit more context. And I'm going to move my video there so you can see the graph a little bit better. It looks like it's hitting the y-axis pretty close right there to negative 13.84. So way down here. And we're just asked for a sketch. Okay. And so why does this make sense? Why does it make sense that the context of the problem? Well, because we know that E is going to be positive all the time. E to any power is going to be positive. Then we've got a negative here. So think about when the pan of biscuits is coming out of the oven, what's going to happen to the temperature? It's going to decrease, right, when it comes out of the oven. So it makes sense. We'll do the biscuits temperature will decrease when the pan comes out of the oven. And this makes sense then that the derivative would be negative. The derivative would always have negative y values. Okay. And so let's go back to our view so you can see the question here. At time t equals 10, what is the temperature of the biscuits? So this is where we're going to do our fundamental theorem. We're going to do the integral from 0 to 10. And I chose these values because we were told a value at t equals 0, and we're wanting to know a value at t equals 10. And we want this of b prime. And that's going to give me the antiderivative of b from 0 to 10. Now, this integral, I'm going to use my calculator for. So I'll switch our view here in just a second so you can see that. But this view, I'm going to plug in my bounds, b of 10 minus B of 0. Okay, so let's go back to Desmos. And so Desmos is asking here, I'm going to do INT for integral. I'm going to put in my bounds 0 to 10. And friends, since I already have the derivative typed there in as f of x, I'll just put in f of x dx here. And Desmos will definitely tell me that. Keeps me from having to type it again. So I get negative 65.817. That's b of 10 minus, now b of 0 we were told was 100. Whoops, don't need that, parentheses. So b of 10, forgive me, I want to type or write 100 for some reason, is going to be 100 minus that 65.817. And that gives me 34.183. And B is the temperature, so that's degrees Celsius. Okay. So again, if you've seen some of my previous videos, it's a good reminder that we can use our calculator in conjunction with us doing the analysis. Okay, one more example for you of this type. We have a cylindrical can with a radius of 10 millimeters, and we're using it to measure rainfall. Now, during the first 5 days of a 60-day period, 3 milliliters have been collected. The height of the water in the can is modeled by the function S, and the rate at which the height is rising is given by S prime. So we want to find the value of the integral from 10 to 15 of S prime. So that means I'm going to use my Desmos calculator again. I get 2 sine of 0.03t dt. Now, friends, if you're using an 84, you definitely can do the same. You can get the 84 to give you the same calculations. You just have to use the second trace menu. Okay, so INT again for integral. Put in our bounds 10 to 15. And now we need to type in our function, which is 2 sine of 0.03t. Close it. Oops, remember Desmos only knows x and dx. And there we go. We get 3.659. Now the units on this, so S of t is measured in milliliters. Okay, so if we did the antiderivative of S prime, we got S. So this is milliliters. Now, what does this mean? Okay, so remember the integral finds the amount of change of S. S is the height of water. So the height of water changes 3.659 milliliters from T equals 10 days. Notice T is in days here to T equals 15 days. Okay. Now, the next question says, at the end of the 60-day period, what is the volume of the water that has been accumulated? Okay. So we need to know how much has changed from the beginning at 5 days when we had 3 milliliters of rainfall and the end at 60 days. Okay, so let's write the integral from 5 to 60 of our S prime. So this is going to give us the height. You know what? I forgot a 1.5 there. So we'll include that here. And we'll fix the other one just a minute. Okay, so I'm going to switch us back to Desmos so we can get to this value. Now I need to adjust my do my integral here, and that's going to require another set of parentheses. So let's put them in there. There we go. And we need different bounds. So let's change those bounds to 5 and 60. Okay, so that means it changed 163.565. Remember, that's the height. Then we were told this only accounts for the change between 5 and 60. We were told during the first 5 days was a 3 milliliter rainfall. So we've got to add that 3 in there so we can get the total change from 0 to 60. And this is in milliliters. Okay. We are looking for the volume, right? It's a cylinder. We've only found the change in the height. So, in order to find the volume, we've got to do the volume of a cylinder. Remember that formula from your related rates pi r squared h. And let me switch our view back so you can see a little bit better. And I've got my radius is 10 milliliters. We were told that at the beginning. And my height is 166.565. And so we can do this easily, multiply by 100 here, move that decimal 2 places back, and we've got cubic milliliters. Now I want to go back and fix this one in the first one because I left off a 1.5 there. So let me fix that. I'm going to switch this back to Desmos so you can see. I'm going to just do the bounds again now that I have the right integral. So there we go. So it's 11.159. Thank you for understanding on that one. Okay, one problem left then. Let's take a look at the last one. The rate at which people enter an auditorium for a concert is modeled by R. Now, notice R is not labeled as R prime, even though it's a rate. I want you to notice this is a derivative. Okay, where R of T is measured in people per hour. Another reason I know it's a rate. VIP tickets were sold to 100 people who are already in the auditorium when the doors open at T equals 0. For general admission ticket holders, the doors close and the concert begins at T equals 2. If all the VIP holders stayed for the start of the concert, how many people are in the auditorium when the concert begins? So we're going to have to do the change in the people entering, and we got to add the VIP. So we've got to have the people, the VIPs, then we've got to have the total number of people who entered. So that's going to be the integral of our derivative here from 0 to 2. Remember that your integral finds the total amount. It adds them all up. Whereas your derivative finds your rate. Okay, let's switch back. Let Desmos do this. I'm just going to erase that one. Going to do the new integral. We're going from 0 to 2, and we're typing in 1,380 x to the second minus 675 x to the third, and that's dx. There we go. So that means that 980 people entered when the doors open, not counting the VIPs. So we get a total of 1,800 people. Okay, so really, really think about that definite integral being your accumulator. It's your total number, the amount of change, the total number of people that entered, the total change, all of those good things. So I hope that helps. I'll link Desmos below just in case you need it. And if this is the first time you're seeing my face, please make sure it's not the last by clicking that like and subscribe button. I'd love to help in any way that I can. Bye for now.